Thank you. So first of all, let me thank the organizers for giving me the opportunity to give a talk in this splendid conference. And yes, I would like to give you some highlights on the results obtained. Some of them obtained, and some of them is a work in progress, together with Ryszard Hrodecki, Paweł Hrodecki, and Michał Eckstein from National Quantum Information Center of University of Gdańsk in Poland. And well, the title is. Can you hear me?
No.
No. It's turned off.
Do you want to carry on with this? Would that be possible?
No, why not?
Just think about the change.
Now you cannot stop me because you have no microphone. Okay, so the title is a bit misleading because throughout most of the talk I will only consider one particle systems, but this is important to understand what's going on. And then on the final slides it will turn out that for the n particle systems everything still works, all the properties are retained, although this is non-trivial. Okay, and also my talk will be mostly commutative, well, almost completely commutative, but nevertheless, this research originally stems from non-commutative geometric considerations of Nicolas Franco and Michał Eckstein. So I would like to thank Luca Tomasini for giving the entire introduction in full detail, so I can only go really quickly through these slides. But yeah, just to briefly recall what was going on. As you know, a Lorentzian counterpart of Cone's spectral triple can be defined in various ways, but one can risk a statement that these various definitions of a Lorentzian spectral triple have a common denominator, some minimal set of data which already allows one to study the causal structure, as Nicolas Franco and Michał Eckstein did. And this data is, well, the triple. The first piece of the data is a dense star subalgebra of a sister algebra with a preferred unitization. What unitization? It's not that important right now. Instead of a Hilbert space, we have to use a Krein space. So a modification of a Hilbert space which takes into account the Lorentzian signature of the metric, together with a faithful representation of the algebra. And the third part, the third piece of the data is an unbounded operator on the Krein space called a Dirac operator, which is essentially Krein's self-adjoint, and also, well, we want this this derivative, this d, when it acts on any element of the unitization, we want it to extend to a bounded operator for any element of the unitization. And of course, well, I'll be mostly dealing with the archetypical example of such a Lorentzian spectral triple constructed upon a globally hyperbolic spacetime, in which we take the algebra to be simply the algebra. Okay, it was you, right? Okay. One. Okay. Okay, so the archetypical example of a Lorentzian spectral triple can be constructed upon the globally hyperbolic spacetime. The algebra is simply the algebra of complex valued, smooth, compactly supported functions. The Krein space is the space of square integrable sections of a spinor bundle on M, because our spacetime is naturally a spin manifold. And the Dirac operator is the Dirac operator associated with the spinor bundle. And what Nicolas and Michał did, and what already Luca Tomasini told us, was to define an abstract algebraic causal relation on the space of states of the space of states on the algebra of the Lorentzian spectral triple, and they proceeded in the following way. First of all, they needed to define the so-called causal cone, or a subset of elements, of Hermitian elements of the unitization, which satisfy the following condition. What does it do? We will see when I get back to the archetypical example in a second. But for now, if we already have defined this causal cone, we can use it to define the causal relation in the following way. If we take any states on our algebra, xi and eta, then we say that xi causally precedes eta if and only if, for any element of the causal cone, if we evaluate the two states on this element of the causal cone, they have to satisfy the following inequality. So how does it look like in the case of the archetypical example, the commutative one? Well, the causal cone turns out to be just a set of all smooth, bounded, and causal functions, where by causal function I mean here something slightly weaker than this notion as it was defined in Luca's talk. I understand, well, in this talk, causal function would be just any real-valued function on spacetime, which is non-decreasing along every future-directed causal curve. So they need not be continuous, they need not be strictly increasing. It's enough if they are non-decreasing. Then, of course, the space of states in this case is simply the space of Borel probability measures by Riesz-Markov-Kakutani representation theorem. And pure states are nothing but the Dirac deltas. Probability measures concentrated on single space-time points, on single events. And then, if we apply this abstract definition to this case, we obtain the following relation for measures. Well, mu, the measure mu causally precedes nu if and only if, for any causal function, the following integral inequality holds. Now, this is just an application of this general definition, but well, when Nicolas and Michał obtained this, they've pondered whether this is really a good. Well, of course they knew it's a good generalization of the standard causal relation, which looks like this. Let's recall what's the standard definition of a causal relation for events. Well, it has to do with the possibility to connect them by means of a future-directed causal curve. Event P causally precedes Q, if and only if they can be joined by means of a future-directed causal curve. So, yeah, I was rather supposed to say this right now, because, well, this abstract definition rather produces the following definition of this relation, and it's not immediately clear that these two are equivalent, that we have really obtained just reformulation of the standard causal precedence relation definition, right? For Dirac deltas, we would obtain a condition that for any causal function, basically this is a definition of a causal function here. So if this is true for any causal function, then the events upon which, then the Dirac deltas concentrated on P and Q should be causally related. So, okay, maybe this is not directly straightforward that these two are equivalent, but it's not very difficult to prove that they really are. But still, remember that this definition was given for states, for mixed states, for probability measures. So one can actually ponder if one can find an equivalent definition for the causal relation between probability measures without explicitly employing causal curves. So, in other words, when I joined the team of Michał and Nicolas, I started to ponder what would be like a closer analog of this definition, of the standard definition of causal precedence relation for measures. Here we are connecting them by means of a future-directed causal curve. Well, here, of course, we are unable, a single causal curve is clearly not enough. Rather, we'd have to join these two probability measures by means of an entire family of causal curves. Well, at least this is what the intuition seems to tell us. Let me also stress that, well, of course, these probability measures can be supported on the entire space-time. They can be, in particular, they can be also spread in time-like direction for now. Right. So the question is how to define an analogous definition of causal relation for measures. And after some pondering, we realized that the best place to look for this analog, for the right definition, is the optimal transport theory, which is now a very, very well-developed branch of geometry, but mostly in the Riemannian setting. The Lorentzian counterpart, the Lorentzian optimal transport theory, is being very intensely developed right now or in the recent years. Well, after some pondering, again, we've come up with the following definition, which works not only for the globally hyperbolic spacetime, but it makes sense for any spacetime. We define mu and nu to be causally related if and only if there exists a joint probability measure, omega, such that which satisfies two conditions. The first condition states no more no less that mu and nu are supposed to be marginals of omega, right? So if we integrate with respect to the first argument, we should retrieve mu, and if we integrate omega with respect to the second argument, we should retrieve. If we integrate it with respect to the first argument, we should retrieve nu. Well, of course, this first condition has nothing to do with causality yet. This is done by the second condition, which simply states that J plus, that is the set of all causally related pairs, is already the set of the full omega measure. Well, here may be some small mathematical caveat. For this object here, for this expression here to make sense, one has to know whether J plus is a Borel subset of M squared. This, to our best knowledge, hasn't been known before, but luckily it is. J plus need not be closed. It is closed in global hyperbolic spacetimes, but in general need not be. But luckily, one can prove that it's a Borel subset, so everything is fine, and this definition is sound. Some more terminology. In optimal transport theory, such joint probability measures which satisfy the first condition are called couplings or transference plans between mu and nu. So here, because they also have to satisfy certain causality condition, they deserve to be called causal couplings or causal transference plans. Let me also notice that this really is a generalization of the standard definition. Why? Well, because if we take mu and nu to be Dirac deltas, then the only coupling of Dirac deltas is another Dirac delta, this time concentrated at the pair, PQ. And then the second condition is satisfied if and only if this pair PQ belongs to J plus, or in other words, if P causally precedes Q. And finally, this relation turns out to retain its properties of reflexivity and transitivity, and also under some rather mild assumptions on the causal properties of the underlying spacetime, this relation, this extended relation, can be even shown to be antisymmetric, making it a partial order, just as the standard counterpart known from causality theory. Okay, to better understand what's going on here, I've already mentioned the intuition behind this optimal transport theoretic definition, but let me, reinforce this with some nice pictures. So the intuition here is that, imagine that this is mu and this is nu, our probability measures. So this definition from optimal transport theory actually tells us, it has this sort of a hydrodynamic interpretation, that it is possible to transport the measure mu, to redistribute it so that it becomes the measure nu, but we are only allowed, during the transport, we are only allowed here to use future-directed causal curves. So, here are two examples of causal curves presented. Of course, they need not be geodesics. These are geodesics, but we don't have to specify them. We don't have to require them to be geodesics. So the picture is more like this, that the entire measure here is transported along some family of causal curves and becomes the measure nu. But in our joint paper with Michał Eckstein, we have managed to find some more characterizations of this relation, which, allow one to get even more insight into what's going on here. One of those characterizations is the following. It is valid, again, not only in spacetimes which are globally hyperbolic. It's enough if they are causally simple, which means that, causal relation has to be antisymmetric, has to be a partial order, and also it has to be topologically closed. In this case, one can show that mu causally precedes nu, according to this definition I presented a few slides ago, if and only if, for any compact subset of the support of the initial measure, the following inequality holds. So one can say that this condition tells us that the probability which is initially contained within this compact subset K cannot escape its future light cone. This is quite understandable. And also what is important in this definition is that recently, together with Ryszard and Paweł Hordecki, we have managed to give an operational interpretation of this condition, which basically makes it equivalent to the requirement of no signaling. I don't want to get into details here because this is still work in progress. We're still ferociously writing down the article. So let me rather move on. Another similar equivalent definition can be also formulated in terms of Cauchy hypersurfaces, this time, of course, for globally hyperbolic spacetimes, so those which admit Cauchy hypersurfaces. In this case, mu can be shown to causally precede nu, if and only if we consider a causal future of any Cauchy hypersurface, the following inequality must hold for any Cauchy hypersurface. This is another characterization. And let me also mention that with this notion, one can give a very natural generalization of a Lorentzian distance, of a time separation, known from Lorentzian geometry, which also kind of becomes married with the notion of a Wasserstein distance from optimal transport theory. We have put forward, again, quite natural definition of something we called a Lorentz-Wasserstein distance. Well, it basically looks like this. Notice that it's, in one way, it's similar to the time separation, to the Lorentzian distance, because of the supremum we're taking here. But at the same time, it's similar to Wasserstein distance in the sense that we integrate with respect to a coupling of the two measures. And of course, we only take into account the causal couplings, the ones which are allowed by the causal structure. So it's supremum if mu and nu is causally related, are causally related, and 0 by definition if they are not. And this quite natural definition, in fact, has already been used very recently for two different purposes, quite independently. One of those is Robert McCann, who actually has used this Lorentz-Wasserstein distances to study the relation between the strong energy condition by Hawking and Penrose and the geodesic concavity of the Boltzmann-Shannon entropy. To be honest, I have just flipped through his paper, so I don't know exactly what he achieved there, but the paper looks very impressive. And another use of this Lorentz-Wasserstein distance has already been put forward by Andrea Mordino and Stefan Sur in their optimal transport theoretic formulation of the Einstein equations. These are both very fresh papers. They're on archive. I think they are still under review in their respective journals. Another application of this formalism, because well, so far we have just presented a nice formalism, a nice generalization of a causal relation, inspired by the noncommutative geometric considerations of Michał and Nicolas, and also inspired by causality theory between point-like events. But how to use it? What's good in it for us? Well, one way to use it, again, quite natural, is to study the causal time evolution of measures. Let me begin by fixing M to be Minkowski spacetime, because it will be easier to understand what's going on. Well, first next to trivial statement that, well, the geometrical object which models the time evolution of a point-like particle is, of course, a world line. So a curve such that if we parameterize it using our favorite time parameter, this curve has to satisfy the following condition, right? If we take two values of our time parameter, s less or equal than t, then of course our curve has to be ordered according to the causal relation. And actually, one can, since we have extended this relation to measures, one can immediately emulate this condition to define, so to speak, a measure theoretic analog of a world line, or rather, maybe it's safer to call it just a causal evolution of measures. So this time we consider a measure-valued map from some interval to the space of probability measures. This time we assume that it's not spread in time-like direction. This time we assume that for every t, mu t is supported on its own time slice, of its own hypersurface of simultaneity. And then we call this function, this map, a causal evolution of measures, if an analog of this condition is satisfied. So this is quite natural to assume, and it can be readily generalized to any globally hyperbolic spacetime, because global hyperbolic spacetimes admit Cauchy temporal functions. These functions also appeared in Luca's talk, but they were called causal functions. So these are exactly the functions, the real valid functions which have past-directed time-like gradient and whose level sets are Cauchy hypersurfaces. So if we choose our favorite Cauchy temporal function, which is a globally hyperbolic equivalent counterpart of a time coordinate, then we can again rephrase both conditions, the condition for a curve to be a word line, and similarly the condition for a measure-valued map to be a causal evolution of measures. This time, we assume that for every t, mu t is supported on its corresponding Cauchy hypersurface, level set of our fixed Cauchy temporal function. But then, of course, one can have a strong objection here and criticize this definition because, well, the whole point in using word lines and the whole point behind general relativity is that, well, there is no such a thing as an absolute time. And there is no such a thing as a canonical choice of a time parameter. There is no such a thing as a canonical choice of a Cauchy temporal function. Both these definitions, and especially this one, seem to, well, very strongly rely on the choice of a Cauchy temporal function, thus making it not generally covariant. In other words, imagine that an observer who has already chosen his or her time parameter or his or her Cauchy temporal function describes some spreading of a wave packet, whatever. Then, of course, his or her family of measures, his mu t's, look like this. Here they are shown with these red solid lines. But then, of course, if another observer wants to describe the very same phenomenon, but using a different time parameter or a different Cauchy temporal function, he or she would obtain a completely different family of measures supported on a completely different family of Cauchy hypersurfaces. So a natural question arises, will they at least agree about the causality of this time evolution of measures? And luckily, the answer is yes. One can find a definition equivalent to this one, which is manifestly generally covariant. And this definition is the subject of the following theorem. So, yeah, this is a picture adapted from Penrose's famous book, Road to Reality. So here we've got a theorem that if we fix a temporal function, and if we consider a map, a measure-valued map, such that for every t, again, mu t is supported in the corresponding time slice, then the following conditions are equivalent. The first condition is just the causality condition from the previous slide, and it turns out to be equivalent to the existence of a single probability measure, but this time this probability measure is on the space of word lines. Of course, this is a very loose statement of the actual theorem. Of course, it's much more precise, but I don't want to get too deep into details here. And from this single probability measure on the space of word lines, one of course can retrieve mu t's for all t's if he or she wants to. So this picture from Penrose's book, actually is a nice illustration of what's going on here. So now, instead of looking what's going on in the sequence of time instants, instead of looking what's going on in time slices, how our measure looks like on every of these time slices, we switch our attention to the word lines along which the transport of probability occurs. So this can be made precise. Let me only comment here that, of course, for this probability measure on the space of word lines to make sense, the space of word lines has to be endowed with the structure of a measure space, of a measurable space, or even better, with topology, and not just any topology. In order for the tools of probability theory to work well, it's good if the topological space of word lines is actually a Polish space that is a separable, completely metrizable space. We've managed to do it. We've managed to endow it with topology of a Polish space, and yeah, and everything works. We've managed to obtain this nice theorem. Okay, I can finally move to n-particle systems. How much time do I have?
20 minutes.
Okay, oh, that's more than enough. Okay, because well, so far the measures I've been discussing. Well, I didn't tell you I didn't tell you the probability measures of what there are. But they can model any probability you like. If only you want your probability measure to evolve causally, this is the right formalism to use. So they can, for instance, come from wave packet formalism. They can come from classical physics, modeling, for instance, a distribution of matter in FLRW spacetimes. Yes, you disagree?
No. Just to be sure that I understand. Before we are speaking. So measure localized on Cauchy hybrid surfaces.
Yes.
So short times.
Yes. Yes.
Oh,
yeah. Or you would like to ask whether it's possible to generalize it to to add some time spreading, right?
For example.
Yes, it is. I mean, you know, okay, this theorem we proved assuming that the measures are supported on time slices, but the very definition of the causal relation makes sense even for measures which are supported on the entire spacetime. Only when we speak about time evolution, well, we decided to restrict ourselves to measures supported on.
For those general measures, can you tell something about the dependence on the time fixed time?
Oh, there is no time function whatsoever.
Sorry?
There is no time function whatsoever. This definition is generally covariant.
The last theorem.
The last theorem, okay. Okay, because okay. Right, okay, right, I know. Yeah, it is generally covariant because, well, a word line is a generally covariant notion, and the probability measure on the space of word line is also a generally covariant notion, right? Okay, you might object that I've been speaking about parametrized word lines, but actually one can deparameterize them and obtain a probability measure on the space of unparametrized word lines, and this is already a generally covariant notion. If one constructs this probability measure, then he or she can choose some different slicing and obtain a different family of measures. Okay.
I'm sorry, I just don't understand its equivalence. It's supposed to be independent of the choice of t.
Yes.
So this measure on the face of word line just exists.
Yeah.
But then the theorem is, you should really put the exists before you put the theorem. The theorem is that the map T is causal if and only if mu T can be recovered from this universal measure by restriction.
Yes.
Is that the theorem? Okay.
Yeah, I mean, well, okay. You can go both ways. So philosophically, you can imagine that what's really there is the probability measure on the space of word lines.
But the existence is not. The existence of these universal measures is not part of the following are equivalent. It's something which just exists. And then the following are equivalent is that T is causal, or the mu T can be recovered from this universal measure.
Yeah, you're right. I think it's not the best phrasing. Yeah, thank you. Okay, so right now I would like to extend this formalism to. I mean, we are interested in extending this formalism to n-particle systems. What do I mean by n-particle systems when it comes to measures? Well, let's go through it step by step. So right now let us fix a Cauchy temporal function. Again, we can discuss the general covariance later. Then, as you know, as already Luca Tomasini mentioned, if we fix a Cauchy temporal function, this already fixes a Garrosh splitting. By a Garrosh splitting here, I mean this smooth splitting, right? So the theorem you said, you also mentioned this strengthening of Garrosh result by Bernal Sanchez, who proven that this topological splitting of Garrosh can be made differential geometric, can be made smooth. So if we fix a Cauchy temporal function, we can actually represent our spacetime in this product form with the metric splitting. Now if we look at this S, at this Cauchy hypersurface, as the configuration space of our single particle, modeled by a probability measure or not, it might be a point-like particle to begin with, we can define an n-particle globally hyperbolic spacetime like this. We just, well, this is just a configuration space of n point-like particles, and if we multiply it by real numbers, we obtain again a Garros, Beran, Sanchez splitted n-particle globally hyperbolic spacetime. This is a definition of this spacetime. I don't claim that there is some deep Lorentzian geometry here right now. And then we can also quite naturally define a causal relation on this n-particle globally hyperbolic spacetime simply by demanding that every particle, from the first one to the nth one, well, can only flow causally. Right? So we say that two n events are causally related if and only if we restrict if the ith event is causally related in the usual sense. And then we can well, apply the very same machinery once again. We can extend this relation to probability measures, employing the notion of a coupling, of a transference plan. And then we can also consider a causal time evolution of an n-particle probability measure. Yeah, right. Simply this time, our measure-valued map is supported on these n-particle time slices. And again, the condition looks just the same. But the natural question is whether it still works, whether this relation retains its properties, retains its characterizations, whether we can discuss the general covariance of this definition, whether this nice theorem about this single probability measure on the space of word lines still applies. And the good news is that, yes, indeed, most of the properties are still valid. This is not a trivial result because, well, some of the theorems required major steps back to the very topological layer of causality theory and checking whether everything works out, still works out if we deal with n-particle setting. So, for instance, the characterizations we've seen in the previous slides are still valid. Still this, right now, of course, I'm considering only the measures which are supported on the time slices. Right now, I'm not considering those which are spread in time because it's quite unnatural to consider such measures because we want, well, we have n particles, so each of them has its own position, but of course they have to share the same time, because other than that we will be completely lost. So we still have this nice characterization with compact sets, the one which can be made operational. It's still true that for any Cauchy hypersurface of this n-particle spacetime, where of course one has to define a Cauchy hypersurface from scratch, the definition is the same as usual. A Cauchy hypersurface, of course, in this context is a subset which is crossed exactly once but by every future-directed time-like curve. One can prove that this is really a hypersurface, and one can also prove this characterization of the causal relation of n-particle measures. And also the original definition of a causal relation for measures, which stemmed from non-commutative geometric considerations of Michał and Nicolas, also makes sense here. For any time function, if such integral inequality is satisfied, then it's satisfied if and only if mu s causally precedes mu t. Well, this is really a time function, so again, a real valid function which is continuous and which is strictly increasing along future-directed causal curves. And finally, it is also true that that this definition that the notion of a causal time evolution of n-particle measures is actually generally covariant, is independent from the choice of Cauchy temporal function, because one can prove an analogous theorem to the one I've shown before, and one can show that the causality of this map is equivalent to the existence of a single probability measure on the nth Cartesian power of the space of word lines. So this space is again, well, it doesn't require fixing Cauchy temporal function. Okay, so let me conclude by, well, recapitulate what I've said and in the form of some take-home messages. So we've managed to naturally extend the standard causality relation between point-like events onto probability measures. And well, this extension can be used to model the causal evolution of probability measures in globally hyperbolic spacetime, which can be summarized in, well, in a remark that just like a single word line is a geometrical object which models the time evolution of a point-like particle, a probability measure on the space of word lines is a geometrical, generally covariant object which models the time evolution of a non-local particle of a probability measure. And it also makes sense for n-particle systems. This formalism still works in n-particle settings. What one has to do is simply to define an n-particle globally hyperbolic spacetime by taking the nth Cartesian coordinate of a Cauchy hypersurface and creating this kind of product manifold. So it relies on the Garros-Bernal-Sanchez splitting, but the notion of a causal time evolution of an n-particle measure turns out to be independent of this splitting. And yeah, let me finish by recalling that, well, this causality theory for probability measures, even though it's commutative, actually stemmed from non-commutative geometric considerations. So it's a nice illustration of the fact that non-commutative geometry can still inspire and tell us something which we didn't know even about the commutative setting of the commutative case. Okay, that's it. Thank you for your attention.